Welcome back to our series of videos on calculus, the introduction to calculus. Last video we looked at the rules, the simple rules that we can use to help us differentiate functions to find the gradient of that function. And one thing I left you with last time was that there are 4 different rules that we can work with to solve. But what we've got here is we're going to be looking at some examples. But before we go to those examples, there's some more things that we need to remember before we start differentiating. So the things that we need to remember is, the first thing is we need to change all fractions into powers. So we change all fractions into powers. So for instance, if I had 1 over x, I need to rewrite this here as x to the power of -1 from our indices rules. The second rule here is that if we have any square roots, so we change all square roots or all square functions. Let's say not square roots, say all roots. So change all roots into powers. So for instance, if we had the cube root of, let's say, x, we'd have to rewrite this here as 1/3 x. And then the last rule that we have here is that if we have terms that are divided by a single term, then each of those terms in numerator are divided by that denominator. So we can do all these things here must be taken into consideration before we do any differentiation. So let's get into these examples I've got in the blue over here and talk them through. So your first rule we have here, we've got y is equal to 7x to the power of 4 minus 3x squared plus 4x plus 5. Let's differentiate this. Now this here is that 4th example where we've got f of x, g of x, h of x, j of x. Each of them are going to be differentiated separately. So we can rewrite this here as dy dx. Now before we go any further, let's check. Do we have any squares or any roots? No. Do we have any fractions? No. So we can just differentiate. So let's do our simple differentiation. 7 times 4 is 28. X, take 1 away, 3. 2 times -3 is -6. Take 1 away from the x squared is x. This here just becomes plus 4. Remember, we're assuming there's a 1 here. So 1 times 4 is 4. 1 take away from this gives me 0. X to 0 is 1. And the last one here is 0. So we don't go any further. So we've got here our derivative of this function up here, y is equal to 7x power of 4 minus 3x squared plus 4x plus 5. Remember the constants. Remember that graph we did? It has a 0 gradient, so it doesn't exist. Okay, so let's have a look at the second example here. Y is equal to x to the power of 5 plus 1 over x cubed. All right. We now need to employ one of these rules here, one of these changes, because I can't differentiate this unless I've got it all in powers. If it was first principles, yeah, go straight ahead, but it's not in first principles. We're using our simple rules. So we need to first get this into powers. So y is equal to x to the power of 5 plus x to the power of -3. Remember our indices rules, okay? If it's as a fraction, we write it as an indice to a negative power of that power in denominator. In this case, the power was 3, so it's to the power of -3. And it's from this point that I can now start differentiating. So, dy dx is equal to, well, 5 times 1 is 5, x, 5 take 1 is 4. I bring my -3 out, so it's -3x, take 1 away is -4. Now, generally when we're working with differentiation, this here is correct, okay? It's an unsimplified version. However, a lot of times you may be asked to simplify it. And if we're simplifying it, we're changing it back to what it originally was. So we can write this here in the simplified version. dy dx is now equal to 5x to the power of 4 minus 3 on x to the power of 4. And this here is the same as this answer, it's just simplified. Alright, let's have a look at the last couple of examples. Y is equal to 4 times the square root of x. Alright, this question here, it's this second one. We've got a root in there. We can't have that root, we've got to write it as a power. So let's rewrite this here as 4x to the power of a half, because the square root of x is the same as a half. Now I'm at a point where I can start differentiating. So let's differentiate this. We get dy on dx is equal to, well, half times 4 is 2. 2x, now if I minus 1 from here, I'm going to get negative half. Now, this here again is the simplified is the unsimplified version. However, we generally don't like leaving things with negative powers if we can help it. Well, we know what the square root of x is going to become. It's going to become the negative of 1 on 2. However, if we look at this function here, we can mix two of these parts up. We can rewrite this here as dy dx is equal to 2 on x to the power of a half. So I'm just reversing this. Instead of now being negative, it's now positive. And the last step is I'm reversing back to my original point. So therefore, dy on dx is equal to 2 on the square root of 2. So this here is the simplified version of this answer up here. But if we're differentiating, this is your function, that's your derivative. Alright, let's look at the last example. So the last example employs that last rule that we haven't written up on the board, but we're going to be working it out. Anytime we have a function where we've got a numerator divided by a common denominator, well, we're going to basically saying that we're dividing this by that. So we can rewrite this here as y is equal to x over x to the power of 3 minus 5 over x to the power of 3. So we're dividing everything by that same value. We're not ready to differentiate because now we're into a position where we have to change our fractions to powers. So if we look at this part here, I can't bring this up and do minus, do x to the power of negative 3, but what I can do is that this is division. Remember, when we're dividing bases, we subtract indices. So this here becomes x to the power of negative 2. And then we can bring this up because this is the same as what we did in this instance before. We've got something over x, so I can bring it up and write it as 5x to the power of negative 3. But this one here, because they're both x's, I'm just going to divide them out. And I get, when I subtract my indices. Now I'm at a point where I can differentiate. So we differentiate, bring the negative out the front, so negative 2x to negative 3. Plus, now remember, a negative times a negative is a plus, so negative 3 times negative 5 is positive 15, x to the negative 4. Again, the non-simplified version. However, we want to try and write it back as its simple form. So we can rewrite this here as dy dx is equal to 2 on x cubed plus 15 on x to the power of 4. So we'll write that as negative, so you can see the negative. So therefore this here is the simplified version of this question. We'll understand the difference between two because sometimes you may ask to write an unsimplified answer or a simplified answer. And they're examples of simple rules of differentiation. Remember, when we're looking at these simple rules of differentiation, the first thing we're doing is we're looking to find out, do we have any fractions in the question? Let's remove those and make those negative indices. Do I have any square roots? Let's get rid of those and write them as an indice. After I've done that, I then start working through the simple rules of differentiation. Times, subtract. Times, subtract. The only time that changes is changes in terms of times and subtract is when we start doing integration, okay? Or when we have a constant. The constant becomes a 0, remember? And the last thing we need to remember when we're working on this here is if we've got a function over a shared function, we need to divide the numerator by that common function and then get rid of that fraction before we can start differentiating. So x minus 5 over x cubed is the same as negative 2 on x cubed plus 15 on x4. This here is the gradient of that function. Alright, I hope that made sense. I'll see you in the next video when we start putting this stuff into action.